Hello everyone, my name is Nitin Panikkar and I work for the Oak Ridge National Lab at the Nuclear Energy and Fuel Cycle Division. Today I'll be giving a talk on the large eddy simulation study of aluminum smelting process using the open source tool OpenFOAM. So the main goal of this project is to utilize information from CFD simulations to improve the efficiency of aluminum smelting process and also to reduce CO2 emissions. So this project is funded by High Performance Computing for Energy Innovation. So this is a platform where industries collaborate with national lab to seek their computation expertise. And in this project, we are collaborating with the aluminum company Alcoa. This is a brief outline of what I'd be presenting today. First, I'll start with the aluminum production process, how aluminum is produced through electrolysis, and the different multi-physics involved in this process that we are trying to model through CFD, and modeling using OpenFOAM, which is a C++ open source CFD code. What are the pros and cons of using that open source tool, and move on to the simulation predictions, geometry and mesh, the flow predicted by the LES, the anode effect, and the 3D vortices inside the electrolytic cell, the temperature distribution inside the electrolytic cell, and finally conclusion and future work. Moving on to the electrolysis description. Aluminum has many applications in our day-to-day life. Alcoa is producing about 70 million metric tons of aluminum every year. So the optimization of this process is key for increasing the yield of alumina from these melting pots. So on the right side, you can see a typical aluminum smelting plant, and this consists of smelting pots arranged in serial. So these are the pots in which the electrolysis process happens and the alumina is produced. So if you see a cross section of this pot, this is how it looks like. So the alumina is fed into this pot using a feeder in the powder form. And this alumina dissolves into this electrolyte and ionizes and forms Al3+ and O2-. Electricity is continuously passed through this cell. So as part of the cathode reaction, the Al3+ ions dissolved in this electrolyte accepts 3 electrons and forms aluminum. And this aluminum settles as a pool on the bottom, as you can see in this video. And as part of the anode reaction, the CO2 gas is formed, and not just CO2 gas, under certain conditions, other greenhouse gases like perfluorocarbons are produced on the anodes, and this is called the anode effect, and we will be discussing this further in the results section, how we are identifying the anodes which are susceptible to this anode effect and which produces perfluorocarbons. Multi-physics involved in a typical aluminum smelting process and its effects. So aluminum smelting process is a very complex process which involves many physics. So some of the physics may not be listed on this slide, but we believe that these are some of the crucial physics which impacts the energy efficiency of the cell and also emissions of the cell most. So in the first video, you can see the CO2 bubbles produced due to the anodic reactions, and this CO2 bubbles moves up due to buoyancy and agitates the electrolyte, which controls the mixing of the alumina powder entering. In the second video, you can see the electromagnetic stirring, or this is the effect due to the Lorentz force produced due to the interaction of the magnetic field and the electricity passing through the electrolytic cell. This again have the characteristic. This again promotes mixing. On the third video, you can see the injected alumina which is getting dissolved, and this determines how it's going to travel through the electrolyte and also reach anode for anodic reaction and cathode for cathodic reaction. On the last pic shows the frozen cryolite. So basically what happens is once the alumina powder is injected, that's going to absorb some heat from the electrolyte, and that results in the cooling or freezing of the electrolyte that produces the small solid clumps, and those solid clumps will settle and disturb this production process. So we are trying to predict the cold spots. So we'll be discussing that later in the results section. Moving on to the modeling using this open source CFD code OpenFOAM. So the smelting process is modeled using the open source CFD tool OpenFOAM. So this is a CFD tool compared to other commercial softwares. It's license free and it can be scaled to any number of compute nodes with no cost involved. And this could be customized for any applications with relative ease in comparison to an in-house code. And the capabilities are not as advanced as those of a commercial code. However, the availability of source code makes it easier to add features in comparison to a commercial code. So the green box here corresponds to the solver which we use, which is called the multi-phase Euler form, which is typically used for 2 or more phases, simulation of 2 or more phases. And the green box corresponds to the features which were already present in this multi-phase Euler form solver, which is the momentum of each phases, heat energy of each phases, and the species transport equations, and also the phase volume fraction equation. And on the right side you can see in the red box, or the yellow and the blue boxes, those were the features which we added from our side. And these are the electrochemical reactions like CO2 production at the anode and the alumina consumption from the bath at anode, and the electromagnetic effects, that is a prediction of voltage and current across the cell, the prediction of magnetic field, and also the Lorentz force produced due to the interaction of this current and the magnetic field, and also the magnetic stirring inside this electrolytic cell. So this tool which we built has a capability to predict other processes also that involve electrolysis, for example hydrogen production or the lithium production. And the multiple physics can be turned on or off using a switch, so that you can study the impact of each physics. And also this open source tool can also be automated to a point that the regular engineers with little CFD background can use it with a few clicks for their design analysis. Moving on to the simulations predictions. Geometry mesh and results. The geometry used for this simulation is given here. This is an electrolytic cell with 32 anodes on one row, so in total 64 anodes. And this is the scale of the geometry is very similar to what is used in an alcohol plant, and these are the feeding arrangements they used. And on the right you can see the mesh used, which is hexahedral everywhere, which has hexahedral elements everywhere. And this had about like 20 to 25 million cells, and this was run in about like 384 cores. On the bottom you can see the gas accumulation predicted by the LES simulation. So large CO2 gas accumulation on the anode bottom is not desired, because that's going to increase the resistance for the current, that's going to increase the energy consumption. So this profile could help improve the design. So you can see that on the periphery of the anode, the CO2 gas accumulation is negligible. The CO2 gas accumulation is maximum towards the center of the anode. And this we notice that this is happening because a circulation or vortex present in this corner is driving the CO2 gas away from this anode. So that led to lower accumulation, especially in this corners edges. So these are the velocity predicted by the LES simulation in the inter-anode spaces, meaning between the anodes. And on the left side here you can see the instantaneous velocity and the streamlines. On the right side you can see the averaged LES time averaged results. So as you can see that there are like multitude of vortices formed here, and there is a CO2 plume which continuously, this vortices keep oscillating in the lateral direction. And the average profile looks like this. And we notice that typically for one cell, we notice, if you ignore the symmetry, we notice about like 3 vortices, 1 here, 2 here, and this corners 3 here. And on the bottom you can see a cross section of the anode cathode space, and these are the velocity and streamlines predicted by LES in this space. And you can see that these vortices, the size or length scale of these vortices are much smaller compared to the vortices found in the interanode space. And as I mentioned in the second slide, the anode effect. So the anode effect happens when the concentration of alumina is not sufficient on the anode for a reaction. And typically when the alumina fraction goes below 0.025, the anode effect happens. So our simulations predicts that the anodes on both ends, those are like 3 plus 3, 6, and 12 anodes, has a tendency to show the anode effect, and we have to Alcoa had to arrange the feeders in such a way that they feed more alumina in this corner to avoid anode effect or greenhouse emissions. On the bottom you can see the 3D vortex structures predicted by LES, and these red spots correspond to the alumina powder getting transported by these vortices. So you can see that the corner vortices generated here is transporting alumina from the feeder to the bottom of the anodes for further reactions. So this is like a self-mixing mechanism. It doesn't require a stirrer. In summary, the CO2 stirring and electromagnetic stirring in itself is enough to transport alumina across this cell. On the right side you can see the cold spots, or the temperature drop due to heat of dissolution, as I discussed in the second slide. And these spots could form solid lumps, and they have to Alcoa have to like design appropriately to minimize this solid lump. So that's all I had for this talk, and moving on to the conclusion of the future work. To conclude, we perform a large eddy simulation of aluminum smelting process using the open source tool OpenFOAM, and we reveal some important flow structures which are never revealed in the literature. Anode effects is assessed, and the anodes that have tendency to show maximum anode effect are detected. The temperature distribution is studied inside the cell, and the cold spots are identified near the inlet and also at the bottom of the anode. As part of future work, we are planning to do further LES study by modifying the feeder locations to determine if the anode effect is mitigated, and also to see how it's impacting the cold spots. Thank you for listening. So if you have any questions, please let me know, or you can send me an email at panicarns@ornl.com. And more details about this can be found in our paper which is in press currently. So the description of the paper is given here. Thank you very much. You all have a good day. Thank you.